Here in this video, we will learn about notations, big O notations. Big O notations is a mathematical concept used in computer science to describe the performance or complexity of an algorithm. Specifically, it provides an upper bound on the time or space complexity of an algorithm in relation to the size of the input data. Understanding big O notation is crucial for evaluating how algorithms scale and for making informed decision about which algorithm to use in different scenarios. Next, we move on to the key concepts of big O notations like growth rate. Big O notations focuses on how the running time space requirements of an algorithm grows as the size of the input denoted as n. It increases the it abstract away constant and lower order terms to provide a simplified view of performance. Next one is upper bound. The big O notations provides an upper limit on the growth rate of an algorithm. This means that it describes the worst case scenario for the algorithm performance. Next one is ignoring constants. In big O notations, we ignore constant factors because they do not significantly affect the growth rate as n becomes large. For example, O of 2n is simplified to O of n. They focus on the highest order terms. When expressing the time complexity, we focus on the term that grows the fastest as n increases. For example, in O of n to the power of 2 plus n, the n power 2 term dominates as n becomes a large. So, we simplify it to the O of n square. Next one is common big O notations. Like common big O notations are O of 1 constant time. Next one is O of log n logarithmic time. Next one is O of n linear time. O of n log n linear arithmetic time. And next one is quadratic time. O of n square. Next one is cubic time. O of n cube. O of 2 of exponential n exponential time and O of n factorial time. These all about common big O notations. The algorithm first constant we coming to the constant time of 1. The algorithm takes the same amount of the time regardless of the input sets, accessing an element in an array by index. And next one is logarithmic time. Algorithms times grows logarithmically as the input size increases. This often occurs in logarithms that divide the problems in half at each step. Binary search in a sorted array. Next one is linear time. The time grows linearly with the input size. If the input size doubles, the time takes also doubles, finding an element in an unsorted array like that. Next one is linear arithmetic time. The time grows in proportional to n log n. This is common in efficient sorting algorithm, merge sort and heap sort. Next one is quadratic time. The time grows quadratically with the input size. This often occurs in algorithms with nested loops, bubble sort and selection sort. Next one is cubic time. The time grows cubically with the input size. This is often seen in algorithms with three nested loops, certain dynamic programming algorithm. Next one is exponential time. The time doubles with each additional element in the input. This is often seen in algorithms that solves the problems by exploring all the possible combinations, like the recursive solution for the Fibonacci sequence, like that. Next one is factorial time. The time grows factorially with the input size. This is typically seen in algorithm that generate all permutations of a set, solving the traveling salesman problem, so using a brute force like that. This is all about big O notations.